Rafał, many thanks for kind invitation and this kind introduction. Okay, so this is a joint work with my colleagues Genki Mura and Paolo Muratore Inaneshi. So my plan is to present very recent result we proved with these guys. And the talk is very elementary, right? The result is very simple to present, very simple to understand, and very simple to memorize. As I said, it's very elementary. If you have any questions or comments, feel free to interrupt me whenever you like. Okay, so this is a brief outline of my talk. So I will start with very basic introduction to maps and generators, both in classical and quantum scenario. Then relaxation relates to spectral properties of generators, and then present the main result of this talk, which is very particular bound for relaxation rates of Markovian semigroup, quantum Markovian semigroup. Then I illustrate this result by very simple example of qubit evolution. Then I briefly comment about the main points of the proof of this result. I will skip all technical details. And then I will show you how to go beyond Markovian semigroup, just considering time-dependent generators. And finally, I will conclude and also show some open problems related to this topic. Okay, so this is very standard scenario when we talk about open quantum system. So we have a system S which is coupled to another system which we call visually environment, well, essentially rest of the world. And this is a total Hamiltonian which governs the evolution of the composite, I mean system plus environment. So we have a Hamiltonian of the system, of the environment, and also the interaction part which governs the interaction between the system and its environment. So we prepare at some initial time very particular initial state of this composite system, which has a product structure. So we have a state of the system tensor, fixed state of the environment. And then we evolve using just unitary evolution of the composite system generated by this total Hamiltonian. Okay, so this is the state of the composite system at time t, and it is clear that it is not, at time t it is no longer of the product form, because in the course of evolution some general non-trivial correlations are built up. And eventually at some moment of time t, we, out of this total state of the system plus environment, we extract the state of the system itself, which is just represented by this mathematical operation of partial trace over environmental degrees of freedom. And what comes out is that the evolution of the state of the system itself is no longer unitary, as you know very well, right? So the evolution of the composite system is by construction unitary and is governed by the total Hamiltonian. However, if we extract the information about system itself, the evolution of the system is not unitary. And it is represented by that kind of map, right? So initial state of the system is mapped to another state, right? And the prescription is given here. So you simply pick up a unitary acting on a composite Hilbert space, right? System Hilbert space of the system tensor Hilbert space of the environment, and you fix some particular state of the environment. And this prescription defines a map which has very particular properties. We say that this map is completely positive and trace preserving, and this object plays a crucial role in quantum information theory because it provides mathematical representation of a quantum channel. And actually, any map which is completely positive and trace preserving, well, there are very nice, quite sophisticated definitions of such a map, but for our purposes, it is enough to memorize this celebrated formula, which we usually call Chrus representation. So any map which is completely positive enjoys Chrus representation, right? These operators K alpha are usually called Chrus operators. And if we add additional conditions that the map is not only completely positive, but also trace preserving, these Chrus operators enjoy this additional property, right? And actually, if the map is completely positive and trace preserving, it can always be realized via this prescription that you extend your system to include another system, well, environment. You fixed unitary operator acting on a composite system, and you fixed state of the environment, right? And a completely positive and trace preserving map can be realized in this way. Usually we call this representation just Steinspring representation, or using more mathematical language, people call it Steinspring dilation, right? Because we dilate the operation from the system to the system plus environment. Okay, so this will be one of the main objects during my talk, completely positive map. So if you compare basic properties of map which is positive and completely positive, okay, so what does it mean that the map is positive? A map is positive if it transforms positive definite operator, just Hermitian matrix with non-negative spectrum, into Hermitian matrix with non-negative spectrum. So suppose that you pick up two positive maps, phi 1 and phi 2, right? However, if you build up a tensor product of such maps, in general, tensor product is no longer positive. However, if you restrict yourself to consider only completely positive maps, then you are on a very safe ground, because the tensor product of two arbitrary completely positive maps is always completely positive. Therefore, if you plan to deal with composite quantum systems, somehow we are enforced to use completely positive maps. Just to show you a very simple example which shows difference between positive and completely positive maps, consider just very simple qubit map, right? In terms of block representation, these three maps just are represented by this very simple prescription, right? So the first map changes the sign of a second component of a block vector. Second map just changes the sign of all components, and third map changes the sign of first and third component. All of them are positive because they preserve block ball, right? But only one is completely positive. Actually, the third one, right? So you see, it's not so easy to decide if you are given a map. It's not so easy to immediately decide which map is only positive and which is completely positive. However, we have very powerful result which enables you to decide which map is completely positive. So by definition, a map is positive if this property is satisfied for all positive operators, right? So you know, to check for positivity of the map is very demanding because we have to check positivity of phi applied to all possible positive operators. However, miraculously, to check for complete positivity, it is enough to check positivity of this extended map, right? Only on one particular operator, which is just projector to maximally entangled state. And this beautiful result was derived almost 50 years ago by Choi, right? So, contrary to positive maps, which requires to check positivity of phi applied to all possible positive operators, complete positivity, miraculously, requires to check positivity on a single operator, which is just maximally entangled state. Okay, now, what we mean by quantum dynamics? So quantum dynamics is represented by a family of completely positive and trace-preserving maps, right? Starting at initial time, which is 0, right? With this initial condition, meaning that initially nothing happens. And we understand this family, well, this family is usually called a quantum dynamical map. And simply it transforms initial state, rho naught, into a state at time t, which represents just the evolution of a density matrix rho. A very particular example is represented by famous dynamical semigroup, which enjoys this composition law, right? And because it's a semigroup, it is uniquely defined by the corresponding generator via the standard formula. And the very property of the generator, which gives rise to a family of completely positive and trace-preserving maps, were derived by this guy, Goryny-Kosakowski, Sudarshan, and Lindblad in 1976. And this representation is given here. So there are two characteristic parts, right? The first one is just the standard part of the generator, which gives rise to unitary evolution generated by the Hamiltonian. But there is an extra term displayed here, where this LK, so-called noise operators, from the mathematical point of view are completely arbitrary, plus collection of real numbers, gamma k, and they are positive, right? So this guys proves that a map, family of maps defined via this formula is completely positive and trace-preserving, if and only if the generator has this very particular form. But of course, there is a classical counterpart of semigroup evolution, which corresponds to famous classical Pauli rate equation. So P is a just probability vector, and its evolution is governed by that kind of equation. This Rij are non-negative constants, which we interpret as, well, essentially transition rates, right? So this is a transition rate from state number J to state number I. And if you just define the family of maps, again via standard formula, you recover a standard stochastic evolution of a probability vector. So for any non-negative t, S of t is just a stochastic matrix. So if you compare these two prescriptions, quantum and classical. So of course, in the classical case, there is no Hamiltonian term. And these two terms represent just jumps between states. And those two are somehow responsible for trace preservation. In particular, if you fix arbitrary orthonormal bases in the d-dimensional Hilbert space and pick up the following noise operators, then you can easily build up the following Lindblad generator, which essentially encodes classical evolution of diagonal elements of your density operator. So using that kind of generator, you simply recover classical Pauli rate equation for diagonal elements, well, which can be interpreted as probability distribution. Okay, so just to summarize, we fully understand the structure of completely positive trace-preserving semigroups that generated by that kind of objects, Gorini-Kosakowski, Sudarshan, Lindblad generators. However, it should be stressed that this representation is not unique, similarly to Krauss representation of a quantum channel. Even the splitting into Hamiltonian and non-Hamiltonian part is not unique. So it is clear that these transition rates, gamma k, for sure depend upon a particular representation we are using. And hence they are not directly measured in the laboratory. However, if you consider solution of a dynamical equation, so the simplest way to represent the solution is to check for the spectrum of the generator. If you know eigenvalues and eigenvectors, right? So in generic case, this eigenvectors x alpha define a basis in the operator space. Therefore, initial density operator can be expanded in this basis, and then the solution looks pretty trivial. Because if you apply e to tl to the initial state, so simply this exponential factor appears in the solution. So it is clear that the evolution of rho of t is fully governed by eigenvalues and eigenvectors of the corresponding generator. So that's why I propose to change a perspective. Instead of consider transition rates which appear in the formula for the Lindblad generator, let us check the spectral properties of the corresponding generator. And what we know about spectral properties. So let me recall celebrated result due to Perron and Frobenius, who proved that if you have a stochastic matrix, then eigenvalues of any stochastic matrix are confined to a unit disk on the complex plane, right? They are symmetric with respect to real line. And there is a leading eigenvalue, which is always 1, so-called Perron-Frobenius eigenvalue, right? So eigenvalues are either real or comes in complex conjugate pairs. And actually, the same pattern holds for positive and trace-preserving maps, in particular, completely positive and trace-preserving maps. So for example, if you consider quantum channel and you ask about spectral properties, again, the similar result holds that in this case we have d squared eigenvalues when the dimension of the Hilbert space is d. So all eigenvalues are confined to the unit disk on the complex plane. And again, there is a leading eigenvalue, which is always 1, right? So this, yes?
Maybe many, yes? I mean, multiple eigenvalues, 1.
Yes, at least 1 is, at least yes.
We can have more.
Yes, this leading eigenvalue, of course, as Rafał pointed out, could be degenerated, right? Yeah. Okay, so these are typical properties of spectra of stochastic matrices and completely positive trace-preserving maps, quantum channels. What we know about spectral properties of generators. Again, they are very similar, both in classical and quantum scenario. Namely, the leading eigenvalue now is always 0. Again, could be degenerate. The eigenvalues are, well, the spectrum is symmetric with respect to real line. But now all eigenvalues are confined to the left hand side of the complex plane. They enjoy this property. So real part is never strictly positive, right? Which we understand very well, because if the real part is strictly positive, then the evolution explodes, right? If you recall this formula, right? Okay, so these are very, very general properties of spectra of classical maps, classical generators, quantum maps, quantum generators. Okay, in particular, spectra of complex, spectra of quantum generators enjoy very, very interesting pattern. If you just check for spectra of random Lindbladians, then we observe that they enjoy very universal pattern, which essentially does not depend on the way you generate these random generators, right, after proper rescaling. So instead of a disk, in this case you have kind of lemon shape, and this lemon shape is exactly generated by Z part of generator, right? Okay, but let's come back to our story about spectra of a standard Lindblad operator. So again, just to summarize, this is key property of the spectrum. That's why let me introduce so-called relaxation rate, which is just minus real part of eigenvalue. Well, you may, instead of relaxation rate, consider relaxation time, which is just the inverse of relaxation rate gamma alpha. Right, so relaxation rate is defined as a minus real part of a, in general, complex eigenvalue. Okay, and now comes our main question. Does complete positivity of the evolution imply any constraints for relaxation rate. And to illustrate this problem, let me consider very simple but pretty general Lindblad generator for the qubit. Right? It consists of very standard part. You have Hamiltonian driving, right? That corresponds to pure dephasing with the rate gamma z. You have another part which is responsible for the pumping process with the rate gamma plus, and dissipation process with the rate gamma minus. In this case, it's very easy to find the spectrum and eventually compute relaxation rates. They're given here. You see that one of the rates, which we usually call transversal one, is doubly degenerated. And you immediately recover this famous relation between transversal and longitudinal rates. So this relation immediately tells us that they are not arbitrary, right? They are not arbitrary. If this relation is violated, the evolution cannot be described by completely positive and trace-preserving semigroup. And in this case, it's very easy to check that this relation can be easily translated to the following constraint for any single rate. So any single rate is upper bounded by half of a sum of all rates. Right? So this evolution can be very easily translated to the famous Bloch equation. For the components of the Bloch vector, x, y, z. And you easily see that to stay within a Bloch pole, which means that to preserve positivity, so to stay within a Bloch pole, which means to preserve positivity and the trace of the density operator, it is enough to know that transversal rate is non-negative and longitudinal rate enjoy this property. However, complete positivity is much stronger, right? This non-trivial constraint between transversal and longitudinal rate has to be satisfied. And interestingly, again, Kimura, more than 20 years ago, proved that that kind of bound holds for all qubit Lindbladians, right? Because dimension is 2, you have 3 non-trivial relaxation rates. You construct, let me call it total rate, and then any single rate out of the 3 is upper bounded by gamma over 2, right? For any qubit Lindbladians. Okay, so now the question is, what happens if you go beyond qubit case? Consider d which is strictly greater than 2. Okay, so in this case, you have d squared minus 1 rates. Okay, so we can define total rate just taking a sum of those two d squared minus 1 rates. Now the question is, could we find a universal constant C, well, which might depend upon the dimension, such that for any Lindbladian, d-dimensional Lindbladian, the universal constraint holds. Moreover, it would be nice to find the C as small as possible, right? And already there were some results. Wolf and Sirac, considering only purely dissipative generators derive some bounds for the norm. Essentially, this bounds implies the following constraint for any single relaxation rate. Then, roughly 10 years after Wolf and Chirac, Kimura with collaborators proved that for arbitrary d-dimensional Lindbladian, the following constraint is satisfied. Right? So they improve Wolf and Chirac by square root of 2. And eventually, we few years ago, we proposed the following conjecture, that any single rate is upper bounded by total rate divided by 2 by d. Right? And in this paper, okay, so this was our proposal, right? For that, for arbitrary d-level Koriny-Kosakowski-Sudarshan Lindblad generator, any single relaxation rate is upper bounded by total rate divided by the dimension of the Hilbert space. Of course, if d is 2, you recover the result for the qubit, right? Gamma over 2.
So
okay.
Was it known in classical case? Or in classical case it's trivial?
Interestingly, there is no bound in the classical case, right? It's trivial. Well, it is a very interesting point. Actually, if you give me, well, suppose I have classical evolution with d states, right? So I have d minus 1 non-trivial rates. If you give me d minus 1 non-negative numbers, I can give you a generator such that its relaxation rates are represented by these numbers. So there is no such constraint for classical generator, yes.
Why cannot you then just make a quantum generator that does mimics the classical thing, and then that would mean you don't have a constraint in the quantum case as well, or it doesn't work in this way?
No, but here I insist that.
Can you repeat the question? Because the questions for the audience are not recorded.
No, as far as I understand, the question was there is no bound for classical, but I showed you how to incorporate classical into quantum, right? But my point is that I expect that this bound holds for all possible, right? Not, well, if I restrict myself to this very narrow class, which somehow recovers classical evolution on the diagonal, for this particular class, no bound, right? But I'm looking for the relation, in a sense, universal, which holds for all possible generators, right? Okay, so what we were able to, already prove is that this bound is tight, right? In a sense that you cannot take this coefficient 1 over d smaller. Moreover, we prove that it is always satisfied for unital semigroups. Unital means that preserves maximally mixed state. Moreover, it is true if you add, well, if you assume that the evolution enjoys some additional symmetries, right? It is true for very special class, however, which is very important in physics. These are so-called Davis generators, which are nothing but standard Lindblad obtained in a so-called weak coupling limit. Right? And moreover, we provided some, well, quite convincing numerics to support this conjecture. However, the proof we were not able to provide general proof. And only recently, a few weeks ago, with these guys, we managed to close the loop. And now I briefly comment about main parts of the proof. Okay, so I will show you that if I take maximal relaxation rate out of the set, this maximal rate is upper bounded by total rate divided by the dimension of the Hilbert space. Okay, so I will skip technicalities. I will only comment about main steps. So the first step is this. Suppose that you know some solution, rho of t, right? Because it's for any t, it is a Hermitian operator with non-negative eigenvalues. You can diagonalize, right? So you have time-dependent eigenvalues and time-dependent eigenvectors. But this time-dependent eigenvalues, this is just time-dependent probability distribution. So you may ask, what is the dynamics of this probability distribution? And you easily recover classical Pauli rate equation for this probability vector, but now with time-dependent generator, right? So the first step is just to translate quantum evolution of density operator into the classical evolution of time-dependent eigenvalues, right? Which can be interpreted as probability distribution. Okay, so the next step, now we use properties of the spectrum of the Lindblad generator, right? And what we observe that in the large negative time, the formula for eigenvalues, which are just probability distribution, is exponentially dominated by the eigenvalue with the largest rate, that one. And this Q is just some bounded function of time, right? So once again, oh, sorry, okay. Yes, so first step, we translated a quantum evolution of rho to classical evolution of probabilities. Then we observe that in the large negative time, probabilities are exponentially dominated by essentially maximal relaxation rate of a quantum generator. And then we use some basic properties of standard Lyapunov theory. So essentially we use very well-known fact that consider a differential equation for x of t governed by some time-dependent generator. Then, having a solution, we define the following quantity, which is called Lyapunov characteristic exponent, right? And then there is a very nice result, which essentially tells us that if the norm of the generator is bounded by some constant m, then this Lyapunov exponent is bounded by the same constant, right? The norm is not specified. It's just arbitrary norm, right? Of course, if you change the norm, probably you change the constant. But the point is that if you know the bound for the norm of the generator, you know the bound for the corresponding Lyapunov characteristic exponent. Okay, and then we observe that this solution for eigenvalues of rho, which are just probability, time-dependent probability distribution, the corresponding Lyapunov exponent for this solution, because of this formula, is nothing but maximal relaxation rate of the original Lindblad generator. So interestingly, maximal Lyapunov exponent for the classical evolution of the probability vector coincides with the maximal relaxation rate of the original quantum generator.
So here Qi is the eigenvector of this?
No, Pi is just eigenvalue, and Qi is just some bounded function of time.
So
Not,
some eigenvector corresponding
no,
to this relaxation rate?
no. What is crucial to compute the Lyapunov exponent is this factor, right? So if you know the exponential factor, you are done. So the point is that Pi of t behaves like exponential factor times some bounded function, which is not essential. Right? So interestingly, Lyapunov exponent for the classical solution coincides with maximal relaxation rate for the original quantum generator. And now we are going to use this result from the Lyapunov theory. If we find upper bound for the classical generator, we know that the similar bound holds for Lyapunov, but Lyapunov is nothing but maximal relaxation rate. So now the last step of the proof is to pick up appropriate norm, right? Because the constant m, for sure, might depend upon the norm.
So to understand, actually to get this result, you ignore completely the eigenvectors. Because this is all the, some kind of, to get the bound, you will not need the eigenvectors at all.
Correct. And look, there are three very standard norms, right? So-called infinity or operator norm. This essentially L1 norm and standard Euclidean norm. And all of them leads to different bounds, right? That one essentially reproduces our conjecture, and the second one gives 2 over d, and the third one square root of 2 over d. But look, if you recall the result I already showed you, this exactly coincides with the results of Wolf and Sirac, right? 2 over d, and Kimura and collaborators, square root of 2 over d. Right? So, summarizing, taking appropriate norm, we managed to show that indeed the conjecture posed a few years ago is true and holds for all D-level quantum generators. Okay, so just to summarize this part, for any Lindblad generator, the following constraint is satisfied. Oh, answering your question, no bounds, right? No bounds. For example, you can, if you give me d minus 1 non-negative numbers, I can construct the following classical generator, and its eigenvalues reproduce just this set. So the bound is purely quantum effect, right? Okay, now how to go beyond semi-group scenario? There are several approaches if we consider quantum evolution beyond Markovian semigroup, but I will concentrate on so-called time-local approach.
So maybe just to sum up this classical problem. So I understand that the issue with this idea that in fact you can model classical in quantum is that in classical we have d rates, while in corresponding quantum model we would have d squared.
Yes, that is true, yes.
And that's why the trivial bound for classical becomes non-trivial for quantum, because we have, for each rate we somehow multiply them, and that's why we will still have this 1 over d, because we will have d times the same relaxation rate. Yes?
Yes, exactly. Exactly. This phenomenon happens. Namely, if you encode this classical into quantum, of course you reproduce classical on the diagonal, but still you have decoherence for off diagonals. And decoherence gives rise to new relaxation rays. And now if you sum up this classical, for classical you have no bound, but if you add those coming from decoherence, altogether they provide quantum bound, exactly like that. Okay, so in the last part I will concentrate on the following master equation with time-dependent generator. Okay, so essentially the generator has a standard form with time-dependent noise operators and time-dependent rates. This is a formal solution. But look, now the rates gamma k of t need not be positive for all t. And one of the problems we are essentially going to solve is to characterize admissible time-dependent generator. What I mean by admissible? Admissible generator is admissible if this formula provides legitimate dynamical map. So it is completely positive and trace preserving for any t. And this is an upper problem. Yes.
I'm always confused by how general this is. Can you write then, any CP map in this form just by postulating time dependence of all these things?
Essentially, yes, right. Essentially, yes. Okay, what I mean that the evolution is Markovian. Evolution is Markovian if it enjoys the following property. We call it divisibility, which means that the map at time t can be represented as a composition of two maps. Map from 0 to S and another map from S to T, where the map from S to T again is represented by this formula. But the key requirement is that this propagator for S to T is again completely positive and trace preserving, right? So we call dynamical map lambda of T CP divisible, or this is one of definition of Markovianity, if this property holds, right? So it can be divided in this sense into two propagators, from 0 to S and from S to T. And actually, we fully understand this class because a map belongs to this class if and only if the corresponding time-dependent generator is of the Lindblad form, meaning that all time-dependent rates are non-negative. Right. Okay, but this nice plot tells you that there are many different ways to characterize Markovianity or non-Markovianity. I talk about dynamical semigroup and the evolutions enjoying divisibility properties, but there are many other approaches. Already this somehow simplified concept of Markovianity enjoys several properties. So assuming that the evolution is Markovian in this sense, we have several nice properties like monotonicity of trace norm between two different trajectories, monotonicity of relative entropy, and other quantities as well. And now the key observation is the following, that if we have Markovian, meaning CP divisible evolution generated by time-dependent Lindbladian, so now the rates are time-dependent. But if the evolution is Markovian, we have the same bound, but now with time-dependent maximal rate and time-dependent total rate. So whenever the evolution is Markovian, in this sense, CP divisible, then the following constraint always hold. Right? So in a sense, well, so first of all, that kind of constraints can be considered as physical manifestation of complete positivity, because complete positivity was very essential assumption. And in a sense, you know, they play similar role as Bell or Legge-Garg, sometimes called temporal Bell inequalities, because Bell inequalities rule out local hidden variable models. Legge-Garg rule out essentially classical description. Similarly, violation of that kind of constraints rule out Markovian evolution of an open system. But there are still several open problems. For example, how one of them is to generalize this constraint for infinite dimensional scenario. You see, it's not very obvious how to do it because we divide over the dimension. But on the other hand, we have infinite number of relaxation rates. We found the constraint for relaxation rates which are defined as minus real parts of eigenvalues. What about imaginary part? Is there any constraints for imaginary part of the spectrum? Could we relax trace preservation, which was essential assumption, and consider trace non-increasing maps? Could we generalize this analysis to include superchannels, right? And there are also several mathematical problems related to the theory of operator algebra. So in this theory, people consider K-positive maps, Schwartz maps, other family of maps. So the question is, could we generalize the bound for other classes of maps? Thank you very much for your attention.
Thank you very much for this very clear talk. So we have time for questions now. Yes, Michał.
Thank you, Dariusz, for a very nice talk. I have some follow-up question, because in stochastic dynamics or open system dynamics, people sometimes study past equilibration and like via tools like Rox-Bolev inequality, modified Rox-Bolev inequality. So and like those Rox-Bolev constants appear in as like runtimes of some quantum algorithms. So do you expect that perhaps it's possible to like derive some bounds on those Rox-Bolev constants that maybe give some more fine-tuned control on equilibration using similar techniques?
Well, to be honest, I don't know. The nature of this constants is different, right? Because the rates I discussed, they are uniquely defined in terms of the spectrum, right? The other constants like this, you know, this Rox-Bolev, they are defined in, the definition is different, right? So, well, in principle, yes, but probably you have to use another kind of technique, because the technique which we use here are directly linked to spectral analysis of an operator, right? It is, yes, for example. Yeah.
Okay. So, more questions. This was a very pedagogical talk, so I
Maybe
think,
too pedagogical.
yes. Okay, so any more questions? Yes, yeah.
So I'm really puzzled that it all follows from Lipanov applied to just the P, which is this time-dependent eigenvalues. So I was thinking of this counterexample. I understand I could take two generators that have the same spectrum, but they have different eigen operators, right?
Mhm.
And then I understand that from your result, so I'm trying to do back engineering. How is it possible that maybe I don't understand what is this P, would this P change for these two cases? Maybe this is the case. In that proof, you have this decomposition on previous slide, right? On P and psi.
Yes.
Exactly. So somehow now I take two different Lindbladians, so have different X, I guess, and Y, but lambdas are the same. But somehow in your derivation, psi doesn't matter at all, and that's my.
Okay, so I understand that you feel somehow uneasy that there is no dependence on eigenvectors. Well, there is a dependence on eigenvectors, but not essential, and it is hidden in Q, right? But so the information about eigenvectors is hidden in Q, but the information which is hidden in Q is not essential when you compute Lyapunov exponent, right? So somehow this information is not essential for the bound.
So is the intuition that the eigenvectors kind of preserve the norm, and this all comes from shrinking, right?
Yeah, somehow, yes.
Okay.
But look, here you ask about very limited information, right? You ask about some relation between real parts of the spectrum, right? Something peculiar, right? So the rest of the information is as I told, hidden in this function qi of t, right? But when you compute this coefficient Lyapunov exponent, this information is completely not essential.
Okay, more questions? So regarding these non-trace preserving maps, it's not trivial, yes? Generalization that you just say, okay, I rescale somehow this relaxation rate somehow, and I get non-trace preserving. No,
it's not fully trivial, because now
I don't have one.
Now you have fully d squared.
Yes, without this
rate,
minus
right?
one.
Yes.
Okay.
You lost this special one, which was 0, right?
And you needed this in the proof, this 0
in this proof, yes.
rate.
In this proof, we need it, right?
Where do you need
but
it?
It seems, well, not so
okay.
obvious to show, but it seems that it can be generalized, right? That you can relax trace preservation and replace it by the very property to be trace non-increasing.
Okay, so some last question. Nobody wants to make me happy. Okay, yes, that's everything is clear. Okay, so thanks a lot, Darek, once again.
Thank you.